All right, let's jump right in. We are talking about what might just be the single most important scientific book ever written. Seriously, this is a book that didn't just explain our world, it literally gave us the language, the rules, to describe the entire universe. And it's all thanks to Isaac Newton's Principia.
And you know, it all kicks off with a question that sounds so simple you could almost call it childish. But it's actually one of the deepest questions you can ask. Why does an apple fall down, but the moon doesn't, right? It just hangs up there circling and circling. What's the deal? This was the mystery that Newton was absolutely determined to solve.
So to really grasp how huge this was, you've got to picture the scene. We're in the late 1600s. The scientific revolution is happening. It's exciting stuff. People like Copernicus and Kepler had already figured out the how. They knew planets moved in these oval shapes, ellipses, around the sun. But the big glaring question was, why? It's like they had the universe's rule book, but the most important chapter was just missing.
And this really sets the stage, right? They had the what down pat. Planets move in ovals. Got it. But they were totally stuck on the why. What invisible force was keeping these massive planets tethered to the sun? And here's the kicker. Could that grand cosmic force be the exact same boring everyday force that makes an apple fall? That was the leap. The giant intellectual chasm nobody had managed to cross.
The crazy part is, the story almost didn't happen. Newton's genius could have just stayed locked up in his own head. But then, in 1684, everything changes. The astronomer Edmund Halley, and yep, we're talking about the Halley's Comet guy, he decides to go and visit the notoriously private Isaac Newton.
And this wasn't just, a casual hello. Halley had a massive problem on his hands. Something about planetary orbits that was driving everyone crazy. And he had a hunch that Newton was maybe the only guy on the planet who could crack it. And he was right. This one conversation, it was the spark that lit the whole fuse.
So Halley gets right to it. He asked this very specific, kind of nerdy question that was the key to the whole puzzle. He basically said, okay, let's imagine the sun's pull gets weaker the farther away you get, following an inverse square law. If that's true, what path would a planet take? Halley was probably expecting Newton to stroke his chin and say, let me work on that for a few months, but that is not what happened.
Newton's answer was just unbelievable. He replies instantly, an ellipse. Just like that. Turns out he'd already solved this massive, universe-defining problem years earlier, while he was bored during the plague. And then he just didn't tell anyone. He did the math, solved it, and tucked it away in a drawer somewhere. Can you imagine? Halley was, as you can guess, completely blown away. He knew right then and there, you have to publish this.
So, you'd think, okay, great, let's get this thing printed. But no, there was a huge and honestly kind of hilarious roadblock. The single biggest reason Newton's masterpiece almost never got published? A book about fish. I'm not kidding. The Royal Society, the prestigious group that was supposed to fund this stuff, was flat broke. Why? Because they'd blown their entire budget on a super fancy, illustrated history of fishes that nobody bought. It was a total disaster. So Halley, bless him, was so convinced this book had to exist that he paid for the whole thing himself, out of his own pocket.
So what was actually in this book that got Halley so fired up? Well, in the first part, Newton lays down the law, literally. He gives us the absolute, non-negotiable rules of motion. And these aren't just like good ideas. They are the fundamental laws that everything, and I mean everything, from a speck of dust to a giant planet, has to follow. No exceptions.
And all starts with three big ideas. Law number one, inertia. Basically, objects are lazy. If they're sitting still, they want to stay still. If they're moving, they want to keep moving. Super simple. Law two, force. If you want to change that, if you want to speed something up or slow it down, you got to apply a force, a push or a pull. We all know this one as F equals ma. And finally, law three, action-reaction. For every action, there's an equal and opposite reaction. You push on a wall, the wall pushes back on you. That's it. Those three rules, they pretty much explain all the motion we see in our everyday lives.
But, okay, that was all just the warm-up. The real showstopper, the main event, comes later in the book. This is where Newton takes those laws of motion and does something incredible. He finally answers that question about the apple and the moon. He unites the heavens and the earth with a single idea, and it is genuinely one of the most brilliant moments in all of human thought. He called it universal gravitation. And the concept is just, wow, it's so simple, but it covers everything. Here it is. Every single thing in the universe that has mass is pulling on every other thing with mass.
So right now, you are gravitationally attracting the device you're watching this on. The Earth is pulling on you, but you're also pulling back on the Earth. And yeah, you're even pulling on the moon, just a tiny bit. The bigger the object, the stronger the pull. The farther away, the weaker it gets. Simple as that.
And this is where the magic happens, all wrapped up in one beautiful equation. This formula proved, once and for all, that the force yanking the apple to the ground is the exact same force that's holding the moon in its orbit. Think about that. The only reason the moon doesn't crash into us is because it's also moving sideways really, really fast. So it's constantly falling towards Earth, but it keeps missing. It's in a perpetual state of falling and missing. The apple and the moon were playing by the exact same rules. For the very first time, the heavens and the earth were unified under one law.
I mean, it is impossible to overstate how big a deal this was. The Principia didn't just tidy up a few loose ends in astronomy. It completely rewrote our understanding of reality. It gave us a brand new pair of eyes to see the universe with.
This book basically invented the field we now call classical physics. For more than 200 years, it was the scientific rulebook. It helped kickstart the entire Enlightenment, this idea that we could understand the world through reason. Because suddenly, the universe wasn't some chaotic, mysterious place run by unpredictable whims. No, it was a machine, a grand, beautiful, predictable machine that followed knowable laws. And get this, even today, if you want to build a skyscraper or send a rover to Mars, you're using Newton's math. It's that powerful.
Just look at this timeline for a second. For over 2 centuries, Newton's physics was king. In the 1700s, it's shaping how philosophers think about the world. By the 1800s, it's the engine driving the Industrial Revolution. It wasn't until 1905 that a guy named Albert Einstein came along and showed that at the extremes, like moving close to the speed of light or next to a black hole, the rules get a little weirder. But for 200 years, Newton's ideas reigned supreme. What a legacy.
So if there's one big takeaway, it's this. Newton gave us the idea of a clockwork universe. That's the perfect image for it. A cosmos that wasn't random, but ticked along with perfect mathematical precision. The implication was just mind-boggling. If you could know the position and speed of every single particle at one moment, you could theoretically predict the entire future of everything. It was this incredible vision of a perfectly orderly and knowable universe.
And that brings us to one last, really interesting question. Newton showed us a universe that was predictable, a perfect clock. But what happens when that clock starts to act weird? What happens when we look at the tiniest subatomic level, or at the scale of the entire cosmos, and realize those perfect predictions start to break down? What does it mean for our understanding of reality when that beautiful, orderly machine suddenly reveals a layer of deep, deep strangeness? Well, that's where the story of modern physics really gets going.